Welcome to UBG Bytes, where we break down the latest in tech and security into bite-sized chunks. Today, we're looking at something pretty significant that, well, it flew under the radar for many people focused on the security landscape, Apple's AxLearn. We're going to peel back the layers on the training infrastructure behind some of the biggest AI models out there, including the ones now powering Apple Intelligence that you'll be seeing on devices and servers. We're going to unpack what AxLearn is, why it's a strategic move for Apple, and dive into its technical architecture, which is quite different from other frameworks you might be familiar with.
That's right. It's a fascinating piece of the puzzle, especially when you think about the scale, just the sheer scale of the AI models being developed today. AxLearn is really Apple's foundational system for building those models. It's kind of the engine room.
Okay, so let's unpack this. At its core, what exactly is AxLearn?
Well, think of AxLearn as Apple's specialized deep learning framework. It's built on top of JAX, Google's numerical computing library. But unlike JAX alone, AxLearn is specifically engineered, really from the ground up, for training massive foundation models.
Massive, like
models with hundreds of billions of parameters, the kind of models designed to run across thousands, literally thousands, of accelerators simultaneously. It's definitely not just a research tool. It's built for production scale.
And this isn't just some theoretical project they talked about, right? You're saying this is actually powering Apple Intelligence models we're starting to hear about.
Absolutely. This is the actual training infrastructure used internally at Apple. It's behind those 3 billion parameter on-device models that are, core to Apple Intelligence functionality.
Like the enhanced Siri or rating tools running right there on your phone or iPad.
Exactly those. And is also used for their larger server-side models that Apple states are directly competitive with models like, say, GPT 3.5. So yeah, it's battle-tested in their own production environment.
That's interesting. You mentioned its core philosophy is different from other frameworks. How so?
Right. Many frameworks, maybe historically, have prioritized research flexibility above almost everything else, letting researchers rapidly prototype really novel architectures. AxLearn takes a bit of a different stance. Its primary focus is on production-ready enterprise infrastructure.
Enterprise infrastructure, meaning?
Meaning it emphasizes systematic engineering practices. The goal isn't just to build a cool model, it's to build it reliably, scalably, and repeatedly. And all this while enabling the creation of genuinely competitive models that also align with Apple's big focuses, like privacy and, importantly, hardware independence.
And this framework just appeared. How did it get released? That seems unlike Apple.
Yeah, that's another intriguing part of the story. Apple quietly open-sourced AxLearn. Put it out there under an Apache 2.0 license back in July 2023. There wasn't a huge press event, no big fanfare, which for a company as notoriously, let's say, secretive about its internal development as Apple.
Especially concerning AI.
Exactly. Especially concerning core AI infrastructure used for their flagship AI features, like Apple Intelligence. Open sourcing this system was, well, pretty unprecedented for them.
Okay, this is where it gets really interesting from a strategic perspective then. Open sourcing this specific framework, the one they use for Apple Intelligence, what does that tell us about Apple's bigger AI strategy?
It sends a very, very strong signal. This is widely interpreted as Apple's declaration of independence, at least in part, from the whole NVIDIA ecosystem.
Independence from NVIDIA? How so?
Because AxLearn is built on JAX and XLA, which is Google's Accelerated Linear Algebra compiler. Crucially, it's not built on CEDA, which is NVIDIA's proprietary platform for GPU acceleration.
So what does that mean in practice for Apple? Fewer dependencies?
It means AxLearn can run optimally on a much wider range of hardware. It's designed for TPUs, Google's tensor processing units, which is apparently where Apple trains their largest models in the cloud. You can also run effectively on Apple Silicon, their own chips, using the JX Nettle backend.
Ah, okay. Optimization for their own hardware.
Precisely. And it can run on various other cloud platforms using GPUs too, but crucially, without being locked into NVIDIA's CEDA stack. This allows Apple to sort of sidestep what some people call the NVIDIA tax, that reliance on expensive, specialized NVIDIA hardware and software.
Right.
It gives them immense flexibility. And, maybe most importantly, it allows them to optimize training specifically for their own silicon. That's paramount for efficiency, especially when you're thinking about powerful on-device AI capabilities.
Makes sense. Where did the system actually originate within Apple? Was it a new project?
It apparently grew out of Apple's internal AJAX GPT project,
Hmm.
This is a pretty ambitious effort, aiming to train models exceeding, I think, 200 billion parameters internally.
Sure.
To tackle a project of that scale, they really needed truly industrial-grade infrastructure, something robust.
And they brought in some serious talent for this, I imagine.
Absolutely. Apple assembled a team that included veterans from Google and Meta's AI platform teams.
Oh, wow. Okay. People who know large-scale systems.
Exactly. People with deep expertise, specifically in distributed training and building large-scale infrastructure for AI. They weren't just building another framework. They were building a system designed to handle the immense complexities of training frontier models at scale. And the result is something capable of training models competitive with the most advanced out there, like GPT-4 Turbo for server tasks, while still being efficient enough to shrink down and run effectively on your phone or device.
Okay, so beyond the strategy and the sheer scale, let's dive into the technical details. You mentioned a key innovation is its configuration-driven architecture. How does that work, and why is it such a big deal?
Right. This is, I think, genuinely a paradigm shift for many developers who are used to building models imperatively, writing code line by line to define the network. AxLearn treats models not as fixed code, but as composable building blocks. That's the key idea. The developer defines and modifies even very complex models dynamically using configuration parameters.
So like parameters in a config file, maybe YAML or something, instead of actually changing the core Python code of the model.
Exactly like that. If you want to experiment with, say, a different type of attention mechanism in your transformer model, instead of digging into the model definition code and rewriting parts of it, you might just change a setting, a string or a value in a configuration file. AxLearn handles the underlying composition based on that config.
Can it integrate other code too, or is it all self-contained?
No, it's flexible. It can even integrate arbitrary Python classes.
Right.
So you could, for instance, pull in components from popular libraries like Hugging Face transformers and plug them right into your AxLearn model structure, all managed via these configuration changes.
That sounds incredibly powerful, especially for managing the complexity in these huge models with, billions of parameters.
It really transforms model development. It moves it away from traditional programming towards what you might call declarative composition. You're declaring what the model should be composed of in the config.
Rather than telling the computer step by step how to build it in imperative code.
Precisely. And this dramatically simplifies managing potentially hundreds or even thousands of large-scale experiments. It also massively boosts reproducibility because the complete model definition is captured right there in these easily shareable, version-controllable configuration files.
You also mentioned lazy instantiation in this context. What's that about?
Yeah, that's a neat implementation detail. Within this configuration system, configurations are treated as partially specified objects. Think of them like blueprints that aren't fully built or materialized into actual running code objects until they're absolutely needed. You can incrementally build and modify these configuration objects layer by layer before the final object is created.
And what does that enable? What kind of advanced workflows?
Well, one really powerful thing it enables is runtime adapter swapping.
Adapter swapping, what's that?
Okay, imagine you have a single, very large core foundation model. But you want it to perform slightly different tasks or specialize on different types of data without having multiple copies of that huge model loaded. With runtime adapter swapping, enabled by this config system, you can load the large core model just once. Then you can dynamically swap in small, task-specific adapter configurations at runtime. These adapters modify or augment the behavior of the core model slightly.
Ah, so you don't need to reload the whole multi-billion parameter model just to tweak its behavior for a specific task.
Exactly. It's much more efficient. And Apple apparently uses this capability for achieving context-aware behavior in Apple Intelligence. So the model's response might depend heavily on the specific context or the app you're currently using, potentially swapping adapters on the fly.
And this whole configuration approach applies everywhere, not just defining the model architecture itself.
Correct. This philosophy, this declarative approach, permeates the entire training pipeline. Everything is managed by a core module within AxLearn called the GSPMD trainer.
GSPMD trainer. What does GSPMD stand for?
It stands for Single Program, Multiple Data, which kind of hints at its role in distributed settings.
Right.
This PMD trainer orchestrates pretty much everything. The model architecture definition, the optimizer configuration, how the input data pipeline works, how evaluation metrics are calculated, checkpointing the model state periodically, logging. It's all managed through these composable configurations. It really enforces systematic documentation and reproducibility across the entire workflow, not just the model.
Okay, so if the configuration-driven approach simplifies defining the model and the whole pipeline. How does AxLearn actually handle the, frankly, mind-boggling complexity of training these massive models across thousands of devices simultaneously? That seems like the really hard part.
It absolutely is the hard part. Distributed training is notoriously complex to get right, especially at that scale. And this is where AxLearn's second key innovation comes in,
Yeah.
what they call the global computation paradigm.
Global computation paradigm. That sounds ambitious, maybe a bit daunting.
It does sound grand, but the actual goal is to simplify things for the developer building the model. Instead of forcing you to write code that explicitly manages all the communication, synchronization, and data movement between thousands of individual chips.
Which sounds like a nightmare.
It is a nightmare. Instead, AxLearn lets developers write their model and training logic as if it's running on a single, incredibly powerful, virtual global computer.
And the system somehow figures out how to chop it up and distribute it across all the real devices.
Exactly that. This abstraction layer is powered by an underlying engine called GSPMD. That stands for General and Scalable Parallelization for ML computation graphs.
GSPMD.
GSPMD is the magic, if you will, that automatically handles all the distribution complexities. The developer provides some high-level hints called sharding constraints.
Sharding, like in the databases, splitting things up.
Sort of, yeah. You provide hints about how the data tensors or the model's weight matrices should be split or sharded across the available devices. Based on these hints, GSPMD automatically figures out and inserts all the necessary collective communication operations.
Like synchronizing gradients between devices or shuffling data around, all that complex stuff.
Precisely. All the operations needed to make distributed training actually work correctly, GSPMD generates them automatically based on your high-level description. You don't have to manually orchestrate all those intricate network calls and synchronizations between thousands of nodes.
What kind of distribution strategies does it support? Just splitting data?
No, it's quite sophisticated. The framework supports multiple parallelization strategies simultaneously. You can have data parallelism, where batches of data are split across devices. You can have tensor parallelism, where individual large matrix multiplications within the model are split across devices.
Yeah.
Sequence parallelism, for handling very long input sequences efficiently. And also fully sharded data parallel, or FSDP.
FSDP, I've heard of that. That splits the model parameters and optimizer states too, right? To save memory.
Exactly. FSDP splits almost everything, parameters, gradients, optimizer states across the devices. AxLearn can intelligently combine these different strategies, data, tensor, sequence, FSDP, to optimize resource utilization across the cluster, all without requiring deep manual orchestration from the user.
Wow, that sounds incredibly powerful for pushing the limits of scale. Are there any public examples of the kind of scale it's actually achieved in practice?
Yes, the documentation and papers mention Apple training their AFM server model, presumably one of their large foundation models, across a staggering 8,192 TPU v4 chips.
8,000 TPUs.
8,192, yeah. Apparently organized into 8 separate slices of 1,024 chips each. That's a scale that very few organizations on the planet can even contemplate operating at. But it serves as pretty solid proof that this global computation paradigm, powered by GSPMD, really does work for truly massive industrial-scale distributed systems.
And this approach also handles other common distributed training headaches, like making sure parameters are synchronized correctly or dealing with nodes failing mid-job.
Yes, that's all part of the abstraction provided by the framework. Developers don't typically need to manually manage how parameters get updated consistently across all devices or how gradients are accumulated correctly. The system, orchestrated by SysPMD Trainer and GSPMD, handles that. It also includes built-in fault tolerance mechanisms, which is absolutely crucial when you're training for potentially weeks or months across thousands of hardware components, any one of which could potentially fail.
Makes sense. You'd lose so much work otherwise.
Exactly. And alongside that, you get monitoring and debugging tools that are designed to operate at the cluster scale. Trying to debug a problem happening on one chip out of 8,000 requires specialized tools, and AxLearn provides capabilities for that.
Okay, so it's clearly innovative in how you define models with configurations and how you distribute the computation globally. But is it actually, production ready? Can you really trust it to run something as critical as Apple Intelligence?
It is absolutely battle-tested. That's one of the key takeaways. AxLearn is currently running in production environments at Apple, powering core Apple Intelligence functionalities right now as we speak. It's not experimental in that sense.
And are the performance metrics telling? Does it produce efficient models?
There seem to be, yes. Apple has highlighted their 3 billion parameter on-device model, which was trained entirely using AxLearn. And interestingly, They claim it actually outperforms several larger, well-known competitor models on various standard
And
benchmarks,
larger models
like Microsoft's Phi 3 Mini, Mistral 7B, Google's Gemma 7B, and Meta's Llama 3 8B parameter model. The fact that their 3B parameter model trained with AxLearn competes favorably highlights that the framework isn't just about enabling sheer scale. It's
Mm.
also designed for practical deployment where efficiency and optimized performance really matter, especially critical for those on-device capabilities where compute and memory resources are heavily constrained.
Right. Beyond just the raw performance, what about the engineering side of things? Managing the code base for models with billions of parameters must be incredibly complex. How does AxLearn help there?
That's where the emphasis on systematic engineering, which we touched on earlier, really comes into play. AxLearn uses a strong object-oriented programming approach, particularly with its module system. This helps organize these incredibly complex models into more manageable hierarchical structures. Think of it like breaking down a huge software project into smaller, understandable components.
Like using classes and inheritance for model layers.
Exactly. Along with things like unique naming conventions that help track parameters and activations during debugging. It supports systematic testing methodologies and allows for incremental development. These are all essential software engineering practices, but they become absolutely critical when you're dealing with systems, these AI models, that are effectively massive, complex software artifacts themselves.
And this SPMD trainer module you mentioned earlier, you said it orchestrates everything. Is it basically a full training suite then? You don't need lots of other tools.
Pretty much, yes. It's designed to be quite comprehensive. It's not just one piece of the puzzle. It provides a full training orchestration solution. It handles the model management, the optimizer configuration, setting up the input data pipeline correctly, running evaluation logic during training, saving model checkpoints for resuming jobs or later inference, and managing all the logging. It aims to be a complete solution, which significantly reduces the amount of external boilerplate engineering effort that teams often need to invest just to get a large model training pipeline up and running reliably in a production setting.
What about deployment? Is it primarily tied only to Apple's internal systems or Google Cloud TPUs?
Well, while it was obviously developed internally and seems very tightly integrated with Google Cloud Platform for their large-scale TPU training needs.
Which makes sense given the JX XLA origins.
Right. It has optimized tools specifically for GCP, reportedly allowing things like one-command deployment to TPU clusters with automatic scaling, monitoring, and job management features. However, the framework is designed to be somewhat flexible. It can also work with on-premise GPU clusters and potentially hybrid cloud on-prem setups. It includes general tools for job management and data pipeline orchestration that aren't strictly tied to GCP, aiming to cover the operational complexities of running distributed training in various environments.
Okay, so considering all these aspects, the configuration approach, the global computation, the production focus, the performance, where does AxLearn actually sit in the broader landscape? How does it compare to the frameworks most people know, like PyTorch or TensorFlow?
Yeah, that's a good question. It definitely occupies a unique space. It's clearly not trying to be a pure research tool like some libraries, nor is it aiming to be a completely general-purpose framework for every conceivable ML task under the sun. It sits quite deliberately at the intersection of enabling research flexibility, specifically for foundation models, and providing the necessary scale, reliability, and engineering discipline required for production deployment of those models. If anything, it leans heavily towards the production side of that equation.
How does it compare specifically, say, against pure JAX?
Compared to just using JAX, or maybe frameworks built directly on JAX like Flax, AxLearn adds that crucial layer of enterprise orchestration. The systematic configuration management, the SPMD trainer for pipeline control, the built-in distributed training abstractions, these are things you'd otherwise have to build yourself or integrate from other tools for reliable, repeatable production deployments at scale.
And versus PyTorch, which is hugely popular.
Right. Compared to PyTorch, which is incredibly popular and known for its flexibility and ease of use, especially in research, AxLearn arguably offers superior built-in scalability, specifically for foundation model training, particularly when you need to combine complex parallelization strategies like FSDP with tensor parallelism. AxLearn also arguably enforces a stronger focus on software engineering discipline, simply due to its configuration-driven design and object-oriented structure. PyTorch offers more imperative freedom, which can be faster for prototyping but potentially harder to manage at extreme scale without rigorous external tooling and practices.
Okay. And TensorFlow, the other big player.
Compared to TensorFlow, which has a strong history in production reliability, AxLearn probably provides more flexible experimentation capabilities, particularly through its dynamic configuration system. While TensorFlow Extended, TFX, offers production pipeline features, AxLearn's approach to composition might feel more integrated for certain types of large model experimentation, while still aiming for that comparable level of production robustness via its engineering principles.
But it sounds like it's definitely not for everyone. There must be trade-offs.
Oh, absolutely not for everyone. There's significant trade-offs. The biggest one is probably the learning curve and the required expertise. AxLearn requires a solid understanding of distributed computing concepts, the intricacies of JX and XLA, and getting your head around its specific configuration system. This makes it considerably less accessible than, say, picking up PyTorch for a standard computer vision project or some NLP task.
Right. Not plug and play.
Definitely not. And the framework's inherent complexity, coupled with the significant hardware resource requirements needed to even leverage its core strengths. Training truly massive models across many accelerators means its practical adoption is likely limited. It's aimed at well-resourced organizations, likely those with sophisticated, dedicated ML engineering teams.
So boiling it down, who is the ideal user for AxLearn? Who should be looking at this?
The ideal user is an organization, maybe a large tech company, a well-funded startup, or a major research institution that needs to train foundation models. Models ranging from maybe billions to hundreds of billions or even trillions of parameters. And critically, for these users, systematic engineering practices are not just nice-to-haves, they're absolutely essential for managing the project's complexity and ensuring reliable, reproducible results in production. Think large language models, massive computer vision systems, complex multimodal AI systems designed to serve millions or billions of users reliably.
And conversely, who should probably stick with PyTorch or TensorFlow for now?
Smaller projects, definitely. Teams that are primarily focused on rapid research prototyping without an immediate clear path to massive scale production deployment. Or teams that simply don't have deep in-house expertise in distributed systems and the JX ecosystem. For those groups, the lower barrier to entry and the vast ecosystems around PyTorch or TensorFlow are likely more suitable and productive for standard ML tasks.
What about the developer experience for those who do adopt it? You mentioned a substantial learning curve. Is there good support?
There is definitely a curve. You're juggling multiple complex systems, JS itself, XLA compilation, GSPMD for distribution, and then AxLearn's specific configuration system and modules on top. It takes time to grasp how they all fit together. However, Apple seems to have recognized this and is clearly invested in documentation. The GitHub repository has conceptual guides explaining the core ideas, practical tutorials, and extensive code examples.
Like a hello world for AxLearn.
More than that, there's apparently a quite detailed tutorial walking through the entire process of training a standard ResNet model on the ImageNet dataset. It covers everything from data loading and defining the model via config, all the way through to deployment and training on Google Cloud TPUs. So that gives potential users a pretty concrete end-to-end example of the full workflow.
How does the setup process work? Is it easy to just install and get started locally?
Well, easy is relative here. It depends significantly on your platform. For local development, particularly if you're on Apple silicon hardware.
Which many Apple developers would be.
Right. It's apparently relatively streamlined because you can leverage JAX's Metal backend for efficient local training and debugging directly on the Mac's GPU. For actual production scale deployment, as we discussed, it's very tightly integrated with Google Cloud Platform. They offer tools aiming for streamlined, even one-command, deployment to large TPU clusters, handling a lot of the setup complexity. The overall workflow, once set up, really emphasizes that configuration-driven, reproducible experimentation cycle with automated validation steps, often built into the training pipeline, defined by the SPMD trainer.
And the community around AxLearn, is it active, growing?
It's definitely niche compared to the giants like PyTorch or TensorFlow. You're not going to find millions of Stack Overflow questions about it. But it seems to be growing steadily within its specialized target audience. Looking at the GitHub stats mentioned in the source material, over 2,100 stars, around 334 forks, starting with about 18 initial contributors, including those veterans from Google and Meta AI teams.
Yeah, that contributor profile is telling.
It really underscores who this is for. Serious practitioners focused on large-scale ML infrastructure and foundation models. Apple itself seems genuinely committed to its ongoing development and is actively maintaining the repository. Crucially, their own internal reliance on AxLearn for powering Apple Intelligence creates a very strong alignment between the needs of the external community using it and Apple's own internal priorities. That usually bodes well for the long-term health and development of an open source project.
So its growth is likely to be more methodical, driven by specific capability requirements rather than just mass appeal or ease of use.
Exactly. Adoption is probably being driven by organizations hitting the limits of other frameworks for extreme scale, or those specifically wanting its systematic engineering approach, or maybe its potential for hardware independence. It's attracting research institutions dealing with huge data sets and models, companies building their own foundation models, and potentially cloud providers looking to offer advanced, non-CDA-based training solutions.
Looking ahead then, what are the broader future implications of Apple making this move? Open sourcing and heavily using AxLearn for such critical internal projects like Apple Intelligence. What does it signal?
I think it signals a few important shifts. Firstly, it shows how major tech companies are increasingly approaching AI and infrastructure. Open sourcing powerful internal tools like this isn't just about giving back, it's often a strategic move.
Strategic how?
To influence industry standards, potentially attract top AI engineering talent who want to work with or contribute to these advanced systems, and to benefit from community contributions and bug fixes, especially when aiming for an alternative to existing dominant ecosystems like NVIDIA's CUDA. Secondly, and perhaps more significantly for the industry, AxLearn's success, particularly at the scale Apple uses it, serves as a very strong proof point. It demonstrates the viability of non-CUDA approaches for training AI at the absolute largest scales.
Right. Using JXXLA on TPUs or even potentially other accelerators.
Exactly. This could genuinely help accelerate the adoption of alternative hardware architectures, TPUs, maybe future custom silicon from Apple or others, perhaps even other GPU vendors trying to compete. It potentially reduces the industry's deep reliance on a single vendor for cutting-edge AI hardware.
Which has interesting implications for supply chain resilience, cost, maybe even security diversification down the line.
Potentially, yes. And finally, the sophisticated engineering practices embedded deeply within AxLearn, the rigorous configuration management, the strong object-oriented design principles, the focus on production-ready distributed training abstractions, this whole approach might influence how other frameworks evolve over time. It sort of pushes the entire field further towards adopting more systematic, robust software engineering practices for AI development, treating it less like purely experimental research scripts and more like building reliable, scalable, maintainable software systems, which is crucial as AI becomes more integrated into critical infrastructure.
That makes a lot of sense. It feels like a maturation of the field in some ways. To try and summarize some of those key design principles you've walked us through, the things that really enable AxLearn's capability and scale, maybe we could think of an acronym like CGP.
CGP. Okay, what does that stand for in your mind?
Well, C for the configuration-driven architecture, making model definition flexible and reproducible. G for the global computation paradigm, abstracting away that immense distribution complexity. And P for its focus on production-ready engineering, ensuring reliability and scalability, CGP.
Configuration-driven, global computation, production-ready. Yeah, I like that. That's actually a pretty concise way to capture the essence of what makes AxLearn distinct and powerful. It hits the main pillars.
Okay, good. Hopefully that helps folks remember the core ideas. That brings us toward the end of this Byte on AxLearn. We've really seen how Apple is leveraging this powerful framework, not just to, fuel their own significant AI ambitions with Apple Intelligence, but also how they're strategically positioning themselves in the broader AI infrastructure landscape, making a clear move towards greater hardware independence and really pushing the boundaries of systematic engineering for training these incredibly large-scale models. Now, for security researchers, pen testers, and red teamers like you listening, thinking about complex distributed systems like AxLearn opens up some really fascinating questions, doesn't it?
It really does. The attack surface potentially changes.
Exactly. How does something like a configuration-driven architecture impact model security? Could there be new kinds of injection vectors targeting those configuration files or the composition process itself?
That's a great question. Or thinking about the distributed nature.
Right. What does training a single model across literally thousands of devices mean for data privacy during training? Or what about potential side channel attacks in that highly distributed, interconnected environment? Could information leak between nodes?
These are the kinds of new frontiers security research needs to explore as these systems become more common.
Absolutely. As these highly sophisticated, production-ready AI systems become more prevalent, really understanding their underlying infrastructure frameworks like AxLearn becomes crucial. Not just for AI developers, but for security professionals aiming to identify new research areas, potential vulnerabilities, and the evolving security implications of AI at scale. That's all for this bite of InfoSec insight. Until next time, stay sharp, stay curious, and keep breaking things responsibly, of course.